Hello and welcome to NewsClick. We are starting a new show that this is not rocket science. And in our first example of this, we'll take the James Webb telescope, which is creating quite a bit of wave around the world. We have with us Professor Sabyasachi Chatterjee, who is an astrophysicist and who will helpfully guide us to whatever we are getting from the media and whatever the images that we are getting from the Webb telescope. Okay, Sabyasachi, this is a big moment for astrophysicists because it has opened a completely new window into both the space that we are observing and also because we are looking at the objects which are billions of light years away, also in some sense a kind of time machine that we are going back into what we are seeing as objects, but which the light of which was emitted maybe even up to 13 billion years ago. So there are these two aspects of what we are seeing as through the Webb telescope. So what are your first thoughts when you see the kind of images we are getting? And what does it mean really for the field of astrophysics? Because this is primarily an instrument of astrophysics, and of course the larger one of the models of physics itself, gravity, whatever the other things which are still to be reconciled within physics.
This is incredible. If I go back to my own time, the 30 years or 40 years ago when I began astrophysics, one could never imagine that such achievements could have been done. And as you have rightly said now, that we can go backwards in time to 13 billion years ago, that is when around the time when the Big Bang appeared. And you can see what happened at that stage, how the galaxies got formed, how stellar formations took place. This is definitely one part of an incredible achievement, and definitely some very complex and illuminating science will come out of it. This is one part. And second part, the nature of the illumination that it gives us, because it is a much bigger telescope than what the Hubble is. And furthermore, it is at a much greater distance to be affected by any other noises or disturbing effects. So therefore, the quality of the data, the kind of details that you get are going to be something which perhaps which could not be matched by any other device that we know of. And definitely lots and lots of interesting features will appear, and they will give us ideas about what happened in different phenomena and different characteristic scales of time and length. So that is definitely going to keep people very excited.
I'm going to go into details of the telescope itself a little later. But first, the three class of things that we have seen. One of it is, of course, that they've taken a small part, very small part, as somebody said, like a grain of sand at a distance of a couple of feet from you. And that has been amplified. And that's the one we are referring to about 13 billion years ago, that you can see that small little slice and see the amount of information that we are able to see on that. And what could be seen otherwise as small smudges have really emerged with their own structures and other issues. So you're really saying what you said, that light which emanated 13 billion years ago, shortly after the Big Bang. So how did the stars form? And going back to the famous statement, God said, let there be light, and there was light. What we really have is a Big Bang, and then we have light. And almost that is the light we are beginning to see. So that's one part of it. The second part of it, the exoplanets that you are going to also analyze. which are possibility, but there's a possibility of water. And there is a possibility in the future of certain exoplanets where we might be able to see other signatures. Is there intelligent life in other planets? Are there intelligent life in other circling other stars? This is the second set of questions that we could probably address. We could see. Of course, there could be many more. And of course, the structure of water when galaxies clash, what is happening there, star formation. So these seem to be the three major class of activities we are likely to see. If we leave out the early Big Bang issues, which we have already discussed a bit, how do you see the other issues? And the fact that the spectra seems to be, though of course people like us really love the images. Of course, this is not the images that the Webb telescope really shows. We have colored it to mapping the frequencies of the infrared to certain things, that visible things that we can see. But the spectroscope, that it seems to be much more exciting for astrophysicists.
Definitely, because there are two aspects in astrophysical observations. One is the imaging part, which tells you the details of the distribution of matter in different parts, their temperatures, etc. Spectroscopy tells us that what is it there, what is the kind of atoms that are there, what are the kinds of molecules that are there. So this is composed of two parts, and very interestingly, it is giving us in the infrared region the data that are coming. Infrared, as you understand, observations are very difficult from the earth, or rather extremely they can't be so much reliable because of the fact that our atmosphere itself will absorb much of the infrared. So hence one needs a telescope which is very far away from the environment of otherwise other kinds of molecules, in order that these backgrounds, heavy backgrounds, do not subsume the details of the molecules that you want to look at. And water happens to be one such. In fact, you go away from the background of water to see the water that is in the background. I would put it like this: it is a contorted dialectical statement, perhaps, but this is what we are surrounded by water, and hence to see the water beyond this background, we have to go away. And this is what this telescope has done in two ways.
What you're saying is we have to eliminate water around the telescope in order to be able to see the water spectra that is coming from space. So that's why this telescope works.
Absolutely correct. And hence, its infrared capabilities have been exploited both for the imaging purpose and also for the spectroscopic details, to say that what kinds of molecules are present, what kind of dust that may be formed, etc., etc. Which means this is another class of problems which may not be related to the Big Bang or the expanding universe. Yes, what happened many billions of years out after that, when molecules started forming, that is another class of problems that it is going to tackle and give us the details, real empirical details as to what was happening.
And that too at a long distance from us, which otherwise we would not be able to look at. And of course, this is true also when you could have, for instance, the black holes formations, then you have black holes merging, galaxies being formed, all of these phenomena. We will learn much more because a lot of this is happening around us. So taking different sets of such objects, we can even get a pseudo chronology of how these things happen.
Yes, and we never thought that it was around us. About 20, 30 years ago, when the Hubble also was first launched, we never knew that we will be so close, so that today you'll use the word, it is happening around us. So this is a great stride, one would say.
So In fact, it's quite amazing when I was looking at the pictures that what was a small little element in the Hubble telescope is blown up now through the what we can see from the Webb telescope picture, and the amount of details now that we can see, which obviously was not possible in the Hubble earlier. So we come to the next question, which is what's the difference between the Hubble telescope and the Webb telescope? And of course, the key issue is that it is not a replacement for the Webb telescope, as you've already said. Webb telescope, as you've already said, it's not a replacement for the Hubble telescope, because the Hubble uses really the visible spectrum, a little near infrared, but this is really the infrared spectrum. And that is the one which is much more interesting from the point of view that you're looking at much more distant objects. And therefore, it's going much further than what the details you could have got from the Hubble telescope. And as somebody has said, it's not a replacement, it's a new instrument.
It is a new in various aspects. One of them, that in terms of the size, it is much bigger telescope than uh, the Hubble. Hubble's diameter is roughly 2.5 meters. That is the light gathering area on which it works. It gathers light over a diameter of about 2.5. This is 6.5, which means roughly it would be about 6 to 7 times more. That is 6 to 7 times fainter objects it can collect the light from and give us the details. This is one part. Second part is, as which you have already mentioned, that it works in the infrared. And Hubble's capabilities in infrared are very, very limited. But on the other hand, there are many, many objects in the infrared that we want to look at. Exactly as you said, the water molecules, the dust, exoplanets, and so on. So their signals in the ultraviolet or the visible, which is the main focus for the Hubble, uh, Hubble cannot detect those objects. For that, real capability is in the infrared, and this is therefore not a replacement, but rather it gives us a new window for us to look at different kind of objects which we did not think that it was possible with Hubble. So that is why a new window perhaps has got opened.
And also because the more distant the objects are, there is what is called the red shift that takes place in the spectrum. So therefore, they get more in the infrared spectrum. So more distant objects, in any case with Hubble, would be more difficult to see.
True, true. This is because the redshift, as the objects go recede from us, their wavelengths, if they emit at a certain wavelength, apparent wavelength to us becomes smaller, apparent wavelength becomes larger and larger. And this redshift will be more and more farther the objects are. So therefore it goes into much deeper area. And as you said, that really close to the origin of the universe, up to that time, with those redshifts, we will be able to see what was happening at that time.
I'm not going to get into the engineering of it, because that I don't think is something that we need to discuss today, that how it was packed in a rocket and then unfolded and assembled in space, how it has a nice little sunshade to keep it cool and all that. Those are engineering details. Today, we're not going to discuss that. But the interesting part of all of this is that there are a lot of unfinished, or I will say, a lot of issues which are still extremely open. And do you think, for example, dark matter, search for dark matter, which we still are on, then there are certain anomalies of how at what speed certain things are happening. And these are, again, depending on the paradigm you choose and what you measure, you seem to get different results. So are some of these issues likely to be settled, or it's an open question whether we will settle them or probably find new questions as well?
Yes, the first part is that engineering details, definitely I'm not very competent. because this is a different, but we know that what is required or what one demands from an engineer. So that definitely has been satisfied in order to ensure that the data that we get is clean and the details can be worked out. And given that kind of data is going to be available, a physicist or an astrophysicist will be more confident as to the nature of the theories that one has to build, or what is the basic physics behind these. It can be on the question of dark matter, it can be on the question of formation of stars, formation of black holes, it can be on the question of formation of galaxies. So things are really not open because nature always throws up surprises, and that has been our history. We think that something is closed, but it opens up something else. But definitely we know what to look for. And from there, what course it will take, we can't predict really.
On a different note, Sabyasachi, this is a discussion we need to have another day, that the instruments are essentially today the products of engineers and scientific community coming together, the both communities coming together, because whether it's a Hadron Collider or it is a Hubble, a Webb telescope, they are really instruments built for the purpose of science, and both have to work together in order to build such instruments. Otherwise, scientists alone cannot tell, okay, you do it, I'll just see the instrument. And the engineers have to understand exactly what you want in order to be able to build it. So it's, in fact, this is what on other discussions with, for instance, Professor Rath, we have been having, that we are moving in the direction of industrial scale science. Science is no longer the pursuit done by one or two people. It's really sitting alone in a lab somewhere. It's really at industrial scale, because the instruments opens opportunities. But to create that instrument, you need both sets of communities to work together and a very large number of people. But that's again a philosophical discussion on another day. The last question is, are there immediate some low-hanging fruits we expect from the Webb telescope?
It is very difficult to say, but definitely the question of the molecule formations, I would say, because what I'm saying, that this is an area, molecule formation, etc. The physics and chemistry of these are fairly well known because of our laboratory experiments here. So that knowledge definitely would be useful in understanding the spectra that you were referring to, right? Dust formations, the dust clouds, etc., their compositions. These themselves are also very important subjects, because I'm not going into the details. The question of dust is a very important component of our galaxy, of the star formation problems, and very many of them. So, with these details, the physicists, astrophysicists will be extremely confident as to how to understand the phenomena. And definitely here you will see that chemistry, which we very often consider as a dirty, isn't it? This
Not
also,
me.
not me
Only the
either,
physicists.
not
Only
me
the
either,
physicists.
not physicists of a certain kind like Lord Rutherford. Okay, without their inputs, many of these phenomena will be completely incomprehensible to us. So I think that is a great unifying factor that is appearing before the world of science.
Okay, on that note, we are going to conclude our session, except to leave with our viewers with also this additional information that unfortunately the James Webb telescope that has been named is after a bureaucrat in NASA who doesn't really have the best of record, because he was also heading it in a period where people with different sexual orientation were hounded out of his organization. And there's a big pushback from women and other people saying that that's a name that should not have been given to this telescope. It should have been named after some astronomer, physicist, somebody who has contributed deeply to the subject, like the Hubble telescope was. But we are left with what NASA has done. We are left, unfortunately, as it is not an international project. This is also much more a national project, though European Space Agency and Canadian Space Agencies involved. It's not like the Hadron Collider, which is a completely international project. So we are hoping that in the future, more such international projects will take place, not such a narrow science being a country's prerogative, but really the of something that belongs to everybody. And the last part is that international cooperation and such issues is also a part of the scientific community's work, particularly when the future instruments like Hadron Collider or the Webb telescope costs billions of dollars. So really, these are not something a country can do on their own. It's better if we do it together rather than compete as otherwise we might. Of course, this is only one telescope. We'll come back with other telescopes to you on other occasions, because astrophysics is continuing to be something which is, I think, going to throw up more interesting results the next 1-2 years than perhaps other areas in science. The Hadron Collider seems to be, has gone, it seems a little cold after the initial confirmation of the Higgs-Boson. We don't seem to have seen many new things coming out of that. Maybe it will. But I think this radio physics, astrophysics, new telescopes, all of this is going to open a lot more window into our past as well as our present. Thank you, Sabyasachi, for being with us and enlightening us on many of these issues.
Thank you very much. Thank you.